In this video, we are going to kind of up the ante on radicals, do a little bit more work with that, but before we get to increasing difficulty, let's start by recalling what we know about radicals, get our brains warmed up. So the first thing we need to remember is that radicals undo exponents, or they're the opposite operation of exponents. So just like division undoes multiplication, radicals undo exponents. So if we had the square root of 3 squared, that's going to equal 3. And if we have the cube root of 2 to the third, then that will equal a 2. If we have the fourth root of 5 to the fourth, then that's going to equal 5. So here again, remember, radicals undo exponents. So the radical index will cancel with the exponent. The radical index cancels the exponent, and we're left with what's there before the exponent is applied. This is really easy to see when it's in exponent form. I skipped over the square root because we don't usually write the index, but it's there. A square root has an index of 2, and then that index of 2 cancels out a power of 2. So all of that is stuff that we've already looked at. What we're going to do to go a little bit deeper in the complexity is we're going to introduce variables to simplifying radicals and see how it works with it. We're working with variables. Alright, so for our first example, part A, let's look at the square root of 4x squared. Now what we saw when we were working with numbers is we could actually deal with the factors individually. In other words, we can think of this as the square root of 4 times the square root of x squared. We know the square root of 4 is 2, and then if we remember that the index, which is a 2, cancels out exponents, then it's safe to bet that the square root of x squared is actually x. And it is. So this simplifies to 2x. And I do want to let you know that what I've written here is not a necessary step, but if it's helpful for you, you can write it. I'm just doing it so you can see the thinking that's going on in my head. Alright, now for part B, let's look at the cube root of 24x to the third. So again, we're going to think of this as two separate radicals. And then the question with the 24 is, what 3 things are multiplied inside the 24? This one's a little harder than the square root of 4, so we're going to resort to doing a factor tree over to the right as side work. So 2 things that multiply to give us 24 are 6 and 4, and then 6 can break down into 3 and 2, and 4 can break down into 2 and 2. Now we want to check back and think about what our index is. Here our index is a 3, so that means we're making sets of 3. Well, we have a set of 3 2's being multiplied inside our factor tree, but the 3 is all by itself. So what that means is that the cube root of 24 is 2 cube roots of 3, because the set of 3 2's represents a 2 to the third, and the cube root will cancel out that cubing. Now, for our other piece here that we separated off, the cube root of x to the third, here it's just easy to see that that index is going to cancel the power, and we'll end up with just an x. Now normally when we have all these pieces and parts, what we end up doing is writing the stuff that's not under a radical out front, multiplied together, and the stuff that is under the radical second, multiplied together. So that would give us 2x cube roots of 3. And then that one's all finished. In C, we're going to look at something slightly more complicated. The cube root of 135 x to the fifth. Now again, we're going to cube root the 135 and the x to the fifth separately. I'm not going to split those apart because you kind of just do that in your head. You just know that you're processing them separately. And I'm also not going to go through the steps on cube rooting 135. So go ahead, pause the video, take a few minutes to figure it out, and see if your result matches what I have. What I'm getting is 3 cube roots of 5. If that's not what you're getting, you might want to double check your work and see how I came up with that. That is not the x part, so we still have the x part. So we still have the cube root of x to the 5th to process. Now in our previous example, we had the cube root of x to the 3rd, and so it nicely canceled itself out. But here, it doesn't match. So what we need to do is think about how that could match. So x to the 5th has 3 x's in it. It just has more than we need, actually. So we could think of that as x to the 3rd times x squared. So I copied everything over because we always want to keep all parts of our problems. But right here is what I changed. So x to the 3rd times x squared equals back to x to the 5th. But it's like I'm unsimplifying it to get what I want. Now, this x to the 3rd, that will cancel out, and we'll end up with just an x. But the x squared part doesn't cancel at all because there's not enough there. A cube root cannot undo a square. You have to have at least 3 things for it to undo. And so we're just left with leaving that as the cube root of x squared. Just like when we had the square root of 2, for example, we decided I can't simplify that any because it doesn't have any triplets, or it doesn't, in this case, it doesn't have any squares in it. Or if it was a cube root, it doesn't have any triplets in it. So it's just left as is. So we're going to do the same thing with variables. If there's not enough copies in there for the index to undo the exponent, then it just gets left as is. Now the last thing we need to do here is write the stuff that's not under the radical out front multiplied together, and the stuff that is under the radical multiplied together. That gives us 3x cube root 5x squared. Alright, so with example 2, we're going to practice this action that's going on with the variables a little bit more. First with part A, the square root of x to the 9. Now remember, with square roots, we're looking at an index of 2. That means that we are trying to undo squares. And the question is how many x squareds are there in a 9? How many pairs of x's can we get out of 9 things? So if I had 9 friends and I wanted to partner them up, they would end up in 4 sets with one person that didn't get a partner, unfortunately. So that's what that's going to look like. I'm going to write this out the long ways. What I'm about to do, you don't need to do as a part of your work, though. So that gives us the square root of x squared times 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 the square root of x. Again, you're just going to kind of go through that thought process in your head, is if I have 9 x's and I need to put them in groups of 2, then I'm going to get a total of 4 groups of 2, and then there's one guy there that's left out in the rain. So sad. So when we simplify each of those square roots of x squareds, those simplify to an x. But the square root of x cannot be simplified any. Collecting all those x's up will give me x to the 4th times the square root of x. And that's as simple as that one can get. So this will be the general process when we are simplifying variables that have exponents attached. The question is we look at the index and ask ourselves how many groups of that size can I get out of the exponent. And the math operation that's happening in your head there when you're asking that question is division. Division is the thing that breaks things into equal groups. So essentially here what I'm doing is taking 2 and dividing it into 9. But we're doing division with remainder. So 2 goes into 9 4 times, which is 8. We subtract those, and that gives me a remainder of 1. You don't have to write all that out, but that's the process. That's what's happening in your head. So that means I'm going to have these 4x squareds, and then my remainder of 1. Alright, let's look at another example for practice. Let's take the fourth root of x to the fifth, y to the eighth. And what I'm going to do for this example is I'm going to talk through what's happening in my head, but I'm only going to write what I actually need to write. So first I focus on just the x to the fifth. And my index tells me I need to do groups of 4. With 5 x's, I can have one group of 4 with one left over. So then that one group of 4 gets fourth rooted into a single x outside the radical. And the one that was left over is left under the fourth root. So this x that's outside the radical was the group of 4 that then got fourth rooted, because a fourth root takes sets of 4s and makes them single. This x that's still under the radical was the single leftover remainder. Alright, so with the y's, we're going to do the same thing. Again, we're making a group of 4. We have 8 things. So if I'm going to put 8 things in groups of 4, that means I can do 2 of those groups. So I can do 2y to the fourth, then fourth root them. That's going to give me 2 y's out from under the radical. But the shorthand way of writing 2 y's is to say y squared, because there's 2 y's being multiplied. So the fourth root of y to the eighth is y squared. I did a lot of that out loud and not written down, so if you need to back the video up and listen to it all again, I encourage you to do so. But to finish it up, we need to write the stuff that's out from under the radical out front, and then the radical stuff on the end. That gives me xy squared fourth root of x. Fancy math. Alright, let's do one more, and then I'll send you off on your own. Let's do the cube root of 2, x to the fifth, y to the seventh. So in this example, we're going to be doing sets of 3. With the 2, the cube root of 2, there's no partnerships in there, there's no tripleships in there. I don't think tripleship's really a word, but let's go with it. So that'll just have to be the cube root of 2. That one doesn't simplify. Now what I'm going to do is I'm going to leave a space, and I'm going to write the cube root of 2 back here. So I'm leaving this space for the stuff that will come out of the radical. And then the stuff that doesn't come out of the radical, I'll fill in under the radical. This is just a forethought way of keeping me from having to rewrite it like I have been doing, where I put everything in the correct order, or the acceptable order. Alright, so let's move on to the x's. So I have 5 x's. I'm going to put them in groups of 3. I can make one group of 3 out of 5 x's. That means I will have 1 x outside the radical. My leftovers, after I make that group of 3, is that I'm going to have 2 x's left over that cannot be cube rooted. Now for my y's, I have 7 of those. With 7 things, I can make 2 groups of 3 things. So I'm going to have a y squared outside the radical, and under the radical, I'm going to have just a y, because that's my remainder. 3 goes into 7, 2 times remainder 1. So let me do that again in red. 3 goes into 7, 2 times with a remainder of 1. Alright, so hopefully you're seeing where all that is coming from and going to. It's a lot of processing, and not once you figure out the pattern, you're just kind of going straight to the answer. But there's a lot of individual processing in there. So take your time, be careful with it, see what you can make of it.